Hello, hello. It is time for lecture 19. 10, 9 equals 19. That's right. 5, 10, 15, 19. Lecture 19, a prime lecture, if I do say so myself. Some of you are wondering, why is lecture 19 so cool? Well, because remember, all the way up to lecture 18, we've been talking about electromagnetism. We finished off just on electromagnetic induction, right? About how magnetism and electricity work together in devices, or when you're moving current around and you've got an inductor and a resistor and you've got a capacitor and you've got a voltage source and things like that. All kinds of cool things happen, and the description of how that works is remarkable. It's super cool. It's a little bit algebraic, but what good is it for, right? It's really good to know these things. And I just want to do that because that will bring us naturally to the next stage of electromagnetism and how we use it in ways even beyond these wonderful technical devices. Okay. And that becomes sort of the capstone of how electromagnetism affects us, because that's how we detect the universe. That's how we see, right? That's how we look at things far away. That's how we get information all around our world, our bodies, the universe. Electromagnetic stuff, good stuff. And we're going to transition into that conversation through the things that we were just finishing up on, the electromagnetic stuff that we were talking over in the past few lectures, right? So let's just finish up that aspect of the thought process, right? By saying, what is the value of these RLC circuit things, right? This is where we left off last time. Sharing the screen one more time with college physics, right? Section 23.12, we kind of had this little conversation about RLC series AC circuits. And we were doing a couple of things, trying to make the fact that they are very analogous on an electromagnetic scale, these kinds of circuits, to the simple harmonic motion that we were talking about, the vibration, resonance frequency, and things like that, force damped harmonic oscillators, those kinds of things that you were briefly exposed to in physics 1, right? Yes, and that is super cool. And if you want to review that, we'll get to that in a moment. I'll give you some suggestions on what you can review. However, for now, right, I want to remind you that this stuff, as weird as it may seem, as odd as it may feel, like so distant, it's hard to grasp this concept of electrons flowing and thus things moving around, moving like a spring, or boing, 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 that kind of thing, right? This is how, I'll just do one example, okay? This is how your cell phone works, okay? When we were talking about how your cell phone, when you, many of you don't remember a time when there weren't phones that you could just tap, and bingo, you wound up being able to make the computer screen do stuff. What? Right? How do you do that without any kind of connecting wires or anything like that? It's because our hands and the phone are designed in such a way to create, literally, things equivalent to RLC circuits, LC circuits, RC circuits, RLC circuits. I mean, it's really pretty amazing how you think about it, okay? Without going deeply into the electrical engineering of it, which is, again, a whole class that we could do for like all of the rest of a semester. I'm not going to do that, but I want to remind you, just think about these things. This is not just some abstract thing that, I'll just like solve a math puzzle and you're done, right? These are useful on everyday level. If you are going to be doing anything remotely resembling some sort of biological science or physical science or chemical science or anything like that, heck, even if you just use a phone, right, you're going to use this kind of technology all the time. When you touch a screen, okay, there are a few ways that this can work. One way is that you have resistance, basically, the electromagnetic resistance. That is a resistance that you have between a couple of layers of glass or other conducting substance that's in your phone. When you touch on it, if you push hard enough, right, then the two pieces of the glass or whatever material either come close to one another or they touch. And then, oh, that changes the electrical system, the electrical map, basically, of your screen. And therefore you get a mark there, a pen mark, right? So those old resistive devices are like when you used to sign, put your signature to sign something like a credit card, like an electronic pad, maybe at the supermarket, something like that, right? So that's a kind of resistance-based thing. And then there's a capacitance-based thing, right? Capacitors, right? Because you hear, right? You have a gentle electric current flowing all through, very, very gentle, right? So you won't get electric shock or anything like that, but it's capacitance. And then what happens is when you touch it with your finger, you have a little bit of electromagnetic field around you too, right? Remember, you have electromagnetism, the electrical flow. So when you touch it, you change the current because the capacitance fluctuates depending on where you touch it. And therefore, because of the capacitance of stuff, that's how your screen works. And then if you want to get really technical with the fanciest type stuff, what you do is you don't worry about the electric field or the electric current, use a magnetic field. So you create induction, what's going on. And so basically using either microinductors or like a system that creates an induction layer, you basically create a magnetic field on your screen. And then when you touch it, you can touch it even 1, 2, or 3 different places, and it can tell the difference. So this is why 1 finger swipes and 2 finger swipes and 3 finger swipes are different, because their magnetic field, right, is different depending on how you've touched it and the way that it can sense, there are 1, there are 2, there are 3 variations in the magnetic field that's right near the screen. I'm telling it completely untechnically, okay? I bet you if I were telling this to an electrical engineer, they might kick me in the shins because they're like, you're so imprecise on this, it's not right. But trust me, it's basically right, okay? The basic point is that electronics, that electrical stuff that you were looking at in the past several lectures, it may seem far away, but you are using it every single day, okay? And so always remember that what you're doing when you're doing the physics stuff, right? And now we're transitioning into this next section, which is even, well, I don't want to say it's more practical and useful, but it's pretty darn practical and useful. And like I said, it affects every aspect of our ability to sense the world around us or to receive information from it. I mean, it's just amazing stuff. So take that with you. All right, realize that all of that electromagnetic stuff, never minding the fact that it generates all the electricity we use, right? It also shows up in these subtle ways in our lives, even when you're doing stuff. So if you know why these things are working, why your electrical medical devices are working, why you can tap on this and that, why you can drag and pull and make these things work, why you can make a phone call, why you can take a picture just by tapping a screen. I mean, that is some pretty wonderful, powerful stuff. And so with that, we move on to that next stage of that RLC circuit thing that connects back to physics 1, that mechanical resonance thing, okay? All right, so let's do that. Remember that we are always finding connections from one kind of physical system to another kind of physical system. And if you see sometimes that in physics 2, things rhyme with physics 1, that's because they do. It's because nature has over time, the universe has used these, just manifests itself over and over again in a really elegant kind of way, which can be explained through mathematics. And that's really what we're trying to do here overall, right? So if you remember this RLC circuit down here, right, it has this idea, well, the force but down motion of the wheel in the car is just boing, 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 boing. And if you remember, there was resonant frequencies about harmonic oscillations. So when you're doing an RLC series AC circuit, what you're basically doing is you're creating the equivalent of simple harmonic motion or forced harmonic motion or forced damped harmonic motion. You're bringing that kind of harmonic motion, the periodic activity, but in an electrical system as opposed to a physical system. And that is tremendously powerful because whereas this system, right, in a car will bounce, right? It will oscillate. It might oscillate several times a second or several seconds per time, right? Depends on the frequency. But even if you're trying to do something really fast on a mechanical basis, right? The wobbling or the wibbling of something mechanical can only get up to, a certain level before your machine just can't go any faster, right? Right now I'm blinking that maybe, my hand is vibrating at maybe 30 times a second, right? Maybe 50 times a second if I'm going really super fast, but that's not slow, but 50 times a second. I mean, if we were trying to figure out really precise timings of things, 50 times a second is not very much, right? So you want to be able to oscillate at really high velocities, very high rates, not speed so much, but how many times you are blinking per second, right? And so using these kinds of circuits, you can make oscillations that are hundreds, thousands, millions of times per second, even billions of oscillations per second. In the highest technology stuff, many billions of oscillations per second. Wow. Why do you want to go so fast? Because that's how your computers and your electronics work. You see, when you are talking about how fast your computer is, right, there's this thing called clock speed. Basically, all of your computer stuff runs based on what ticks. There are ticks that are going on inside the electronics of your system. And the faster it ticks, the faster you can move, right? Run how accurately you can keep your watch, right? Stop your watch and stuff. But normally we human beings don't really care a difference between 1 nanosecond and another nanosecond. But when you have a computer, like the one that you may be looking at right now, or the one that I'm using right now to make this recording, what really happens is that everything that I'm doing right now, all the things being captured in fractions of a second, hundreds, thousands, millions, maybe even billions of a second, right? So those operations are happening because there is an oscillation happening on a regular, reliable basis that's making all of this stuff work. That clock speed, like how fast, how many megahertz, how many gigahertz is your processor, right? Those kinds of things depend on your ability to make these oscillations fast and successful. But they're basically, in the end, still oscillations, right? And that's the key word for the rest of this lecture, oscillations. Remember those oscillations from Physics 1? The simple harmonic oscillations, the waves back and forth, right? You may have gotten this in Physics 1, depends on where you took it and so forth. But in the same way that these clock speeds in a CPU chip for your computer, for example, dictate how fast things go and when, in a mechanical system like a car engine, if you have a timing belt, that's the same kind of thing. Every time as a timing belt spins, it very fast, right? Thousands, tens of thousands of times per minute, for example. Then you wind up having the car do this or do that. The engine does this, it does this piston stroke, it does that little thing. All that stuff is dependent on a clock that moves forward. It's based on oscillations. Okay, so in this case, I want to remind you, in case you forgot about oscillations and you want to go back and remind yourself, feel free to do that. And you do a pretty good job in the OpenStax textbook. All right, there's the oscillation stuff, and that's typically in chapter 16. So those of you who've taken Physics 1 already using this College Stacks OpenStax textbook, be like, oh yeah, that stuff, right? Chapter 16, Hooke's law about simple harmonic motion, simple pendulum, energy in a simple harmonic oscillator, all that kind of thing, uniform circular motion, damped harmonic motion. This is a pretty good review of that sort of stuff. And then, of course, information about waves. That stuff was all pretty good. So you're welcome to look through that and remind yourself, oh yeah, here are some of the key equations, here are some of those things in general, right? Because we're going to go to specifically electromagnetic waves and circular motion, and oscillations in the electromagnetic world, and that leads to light, leads to X-rays. I mean, it's amazing stuff. We can't wait to talk about that. It's just so much great stuff. But if you want, again, to remind yourself about these things, I'll remind you also that the Wikipedia page for simple harmonic motion's got some great graphics and good explanations. It's a little bit technical, and for those of you who aren't familiar with calculus, some of this technical stuff will be harder to understand. But remember, no need to be afraid of calculus or anything like that. It's just additional cool mathematical stuff, right? You just remember that there's the change in position, right, or displacement is called velocity, and that's the change in velocity is called the acceleration. And so that the change in the change in displacement is therefore acceleration. So it's that kind of layering of mathematical concepts in there, and it's just a discussion of it. And if you don't want to get too technical on this, you can read this and remind yourself about simple harmonic motion and how you have, as a result, this sort of analogy between linear motion with a restoring force like a spring and uniform circular motion like you've done before with something spinning on a string or something like that around an axis. And if you want just that reminder in a nice high quality physics video presentation with a high production value and a really effective, in my opinion, communicator of physics, watch this. Okay, this is the simple harmonic motion AP Physics 101 stuff that Diana Cowan, who is Physics Girl on YouTube, has created. This is really good stuff. And again, this is a conversation much like what we're talking about here, but it's a review of that stuff, and it's really good. So simple harmonic motion in her Physics 101 thing, and then over here, waves, light, and sound, Physics 101 thing also. And you're welcome to watch them. And I encourage you to remind yourself what it was like to talk about waves and oscillations and things like that. Okay. All right. So if you can get that, go ahead and, if you want to remind yourself, oh yeah, I better get that reminder, go do it now. It'll take about an hour. Okay. Go ahead. I'll be back. Well, you'll be back. I'll be back. Okay. All right. You're back. Or you're like, oh yeah, I remember that stuff. I don't need to review. It's 100% okay. Let's go with it then. Okay. You got those electromagnetic oscillations in your circuits, right? You got the R and the L and the C. In other words, you're having magnetic fields interact with electric fields, interacting with electric current and things like that, right? So you're having all this cool mix of this electromagnetic force expressing itself in different ways. Well, guess what happens when you do it in a specific way? You basically can wind up propagating electromagnetic force. Wow. This is getting fun. Okay, let's get to the textbook and I can show you that aspect of things. Okay, you ready? Remember, we are going full speed ahead, but I encourage you to step back, and anytime you're like, okay, you're writing your notes now, right? I hope you're writing your notes now. Yes, understanding those things. If there's anything that needs clarification or whatever, write it down, check it out. Yeah, ask questions, and we will go forward with it. All right, but remember, these are the key concepts that are so important as far as sensory perception is concerned, about eyes and things like that. In Physics 1, you may remember how waves affect our hearing and how we can hear because you have waves in the air, acoustic waves and vibrations and things like that. Okay, good. Now we're doing that for electromagnetism, and what you get out of that is light. Pretty cool, right? All right, let's do this. Cool review stuff. I'm going to remind myself how I'm going to share this screen here. Go there, and then hit share screen, and then hit this. All right, here we go. There's your wave reminder, everybody. 16.9, right? Remember how waves work, very generally speaking. You have waves like go from peak to peak or trough to trough, for example, right? Dense to undense, depending if you're using acoustic waves or something like that. And the wavelength is basically measured from peak to peak, like the high amplitudes to high amplitudes or low amplitudes, something like that. Meanwhile, your wave travels, right, at some velocity of the wave, and the velocity of the wave is related to the wavelength and the frequency, how many waves pass by a certain location at any given time. V equals F lambda. Remember that? Yes, very important stuff. Remember that, like in most waves, the material doesn't actually move very far, right? The disturbances is what the wave is. It's not the actual stuff moving, right? That's like might be a pulse or something like that. Particles can move under certain circumstances to transfer energy. However, for waves, what they're basically doing is the material, like this in this slinky thing, the wave, this particular piece of the slinky is just moving up and down, up and down and up and down. But the disturbance in the slinky, the wave, is transferring energy over here. So even though I'm wiggling this thing just up and down, right? What will actually happen is energy goes horizontally following the wave at the velocity F times lambda, right? The frequency times the wavelength. So again, review this if you want. It's very straightforward. And to remind yourself, that we're talking about. Now, in the acoustic waves, right, you have a guitar string. It's a transverse wave. The guitar string is waving back and forth this way, but what it does is it pushes sound, it pushes air at that same frequency. So that air is coming to your ear with that frequency. So it's like wah, 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 wah through that way. And that's why you get sound that you can hear. The power, the energy in that case is distributed when the medium, in this case, the air, or if you're listening underwater or whatever, that medium is transmitting the energy to you. Okay, so that's kind of the key basic points about waves. And then you can read 16.10 to remind yourselves that waves have these phenomena called superposition and interference, right? Which I will only click on and zip right through to remind you. Remember, it's not really worth your time for me to just read the textbook, right? But just remind yourself, go through and see all these cool things, right? Waves, just in a string, for example, are really straightforward, but you can add waves, you can subtract waves, and sometimes they go in different directions. And when you superimpose waves, it's like superimposing a lot of sounds, right? Think about that. You've got high pitches and low pitches and medium pitches together, and it sounds all together and like an orchestra. It has its combined sound. This is true for all kinds of waves. Specifically, you can create these loops, right? And nodes and antinodes, and then first tones and second tones, which are all cool stuff about music, which you should all listen to because it's fun, right? But this works also for light. And then the last thing about waves, just as a reminder, right, is that you carry waves. In waves, you carry energy. How much energy? We'll talk about that, right? These are intensity of a wave, power per unit area. In our ears, right? This is something that you probably did again in physics 1, but I'll just zip right through and remind you that the ray of sunlight, right? The average intensity of sunlight at Earth's surface is about 700 watts per square meter. Full intensity sunlight is 1400 watts per square meter. Okay, so it's double this roughly. And about half the time it's not there, right? Because Earth is spinning and therefore you don't get all that all the time. So that's also there are clouds, and also some of that intensity of those waves of energy, right, do not come in energy levels that we can see. That's coming up, electromagnetic waves, right? Some of this you've already heard of before, but it is super fun and cool. So you got to make sure to know some of this stuff. Okay, so combining the intensity and all this cool science, and then you have this sort of thing. Like, for example, if you're making, remember, constructive and destructive interference, right? So if you're doing a concert hall or something like that, some areas are rarefied, or that is like less pressure or less stuff, and some areas are compressed, which makes it more dense, right? So the waves that are coming through, you end up creating areas of high sound and areas of low sound, or in the case of light waves, areas of bright and dark. We will talk about this. Yes, we will. It's all there. So remind yourself about this, okay? Energy. And it's definitely worth spending this time to remind ourselves about waves and about oscillations, because this is going to be the rest of the cool science, because we're going now to this part. 24, chapter 24, electromagnetic waves. Okay. And now we are connecting back from what we did in the past few lectures, heck, most of this semester for that matter, for this term, right? Which was about electric fields, magnetic fields, and things like that, and circuits, and waves, which you learned in physics 1, because it turns out you can make electromagnetic waves if you've got the right combination or the interaction of electric fields and magnetic fields in a system. Wow. Okay, so here is some stuff coming in now, and I want you to watch this, as the textbook is pretty good on this, and it's kind of worth watching and see how your stuff that you learned up to this point in this section causes waves to happen. All right, again, I'm not going to read the textbook to you because that's not a good use of your time, but I'm going to hit the highlights. I want you to go back and read. I hope you're already taking notes on this stuff, right? You're going to go back and read the textbook a little bit more carefully as I'm going through, so that you can understand, oh, this is what it is. Like, internalize your understanding of how these electromagnetic waves are created. Okay, here we go. Now, here's an introduction to electromagnetic waves. This is chapter 24 in the college physics OpenStax textbook. Okay, and so this is a cool picture. Human eyes detect these orange sea goldy fish swimming over a coral reef in blue waters of the Red Sea using a visible light. That's right, because that's waves, all right? And the different waves that they bounce, when they bounce off the coral or they go through the water or they bounce off the fish's scales and stuff like that, or the eyes or anything, you wind up getting electromagnetic waves to your eyes. These electromagnetic waves, you make them. How do you make them, right? So Maxwell's equations, what happened was there was a guy named James Clerk Maxwell. Okay, Clark is spelled C-L-E-R-K. So like in America, we would pronounce him Clerk, but he's British. And so he's named James Clerk Maxwell. But Maxwell, basically, who was a physicist of great renown in the early-ish to mid-ish 1800s, said, you know what? If I take Faraday's ideas and I take Ampere's ideas and I take Ørsted's ideas and things like that, I can see how electromagnetic waves are a lot like acoustic waves or waves in a string or waves in a spring and things like that. And he started relating them together and trying to show how that all happened. Turns out that over time, Maxwell's equations were refined. A guy named Heinrich Hertz, H-E-R-T-Z, you know the Hertz guy? Yeah, him. He will wind up, and others wind up saying, you know what, Maxwell, you were right. Let's adjust them and really, take them into the realm of understanding electromagnetic waves in the context of electromagnetism, as opposed to the context of mechanics, right? And so really things blossomed in the 1800s, and by the 1900s we were using electromagnetic waves effectively, but still building things like radar, for example, was developed in the 1930s and 1940s. That's electromagnetic radiation waves, right? And then radio, AM, FM, ham, all those kinds of things, not to mention things like x-rays, television, all that wonderful stuff that we have today, now all this wireless stuff, it's all electromagnetic waves. So that's important. How do you produce electromagnetic waves? And then you have the electromagnetic spectrum. Oh, and then the energy in electromagnetic waves. When we get to chapter 24, section 4, 24.4, we are starting to get into a new realm of physics, because at that point you realize, oh, wait a second, there is this thing called quantum physics, because light particles and light waves are the same thing. They both exist simultaneously. There's a tremendous amount of physics there. Oh, it's so beautiful. I would so want to show you all these things, but we just don't have enough time in the course of the semester. I wish we did, but that's okay. You can always take another class in the future, or you can go online and watch stuff. I want you to try this stuff because it's really, really cool. Okay, so here we go. James Clerk Maxwell, regarded as the greatest theoretical physics of the 19th century. Yeah, one of the greatest for sure. There were some others. Thomas Young, for example, was pretty amazing. Never mind. Let me not get into who was the greatest. But anyway, the folks who wrote this textbook really feel like he was the greatest. He's certainly one of the greatest. I have no argument with that. Okay, so anyway, Maxwell developed this thing called the kinetic theory of gases. Oh, yeah, remember that? That's also from Physics 1. We talked about pressure, PV equals nRT, and how they move and how the different objects, when they bounce off each other and things like that. Yeah, and then things like vision, right, which has a lot to do with electromagnetic waves and so on, right? And he also, yes, did astronomy too, which is cool. I'm a big fan of that. So here's the thing that he talked about earlier, that I mentioned earlier, right? Maxwell brought together Ørsted, Coulomb, Gauss, Faraday, all these different people's names, and to build this idea of electromagnetism. Here's Maxwell's equations in word form, okay? Word form. Now, this is cool. You got electric field lines, you have magnetic field lines, and check this out. If you change your magnetic field, you produce electromotive force. That's huge, right? And you also create an electric field. This is basically the Faraday's law of induction and Lenz's law that we talked about before, that you kind of remember, right, from the earlier on in the few lectures that we did in the past, I don't know, most of the past term or so. And then you have this fourth point, which is really cool, right? You get magnetic fields generated by either moving charges or when your electric field changes, all right? changing electric fields creates magnetism. Now, this stuff is, you've already kind of seen, like I said, all four of these things is stuff that you've known before. Now, when you wind up with this point, changing electric fields creating magnetic fields, right, which is a very simple, similar, shall we say, to Faraday's law of induction. And what happens is you can then wind up moving stuff all around and doing neat things. Now, this is an interesting sort of side effect. Some of you who have read this textbook in previous courses, there's up in the earlier chapters about the unification of forces and symmetries and things like that, right? That's really cool stuff. There's a physicist named Emmy Noether from the early 1900s, and she was a person who was able to show that symmetries have everything to do with the laws of physics, like everything that works in these kinds of laws that we have been talking about all semester long, right? These laws up here, they're usually having to do with symmetries. And electricity and magnetism have this beautiful symmetry that's involved, which is really, really nice to have. Now, take a look at here, all right? This is the point that Maxwell was trying to explain. When you have AC circuits, oscillating charges, they produce changing electric fields. And that way, if they're changing electric fields, they're also producing magnetic fields too, right? So what you would do is that if you keep changing fields, all right, like say you have an AC circuit or something, you produce changing electric fields. Each electric field that you generate, it keeps changing, and therefore you create magnetic fields as well. And when they change back and forth, if they change periodically, if they keep changing in a way that's predictable, right, then you actually wind up having this energy go away from your source. You would actually send these waves out electromagnetically, just as if you were like, dropping a pebble in a pond and you have waves of water coming out. Instead here, what you're doing is you're disturbing your electromagnetic environment, right, by changing your charge, right? And change your magnetic field, changing your electric fields, and all that together will cause energy to radiate out in waves. Are you kidding me? Wow. And then what he said was, well, the speed at which they would go out, right? Remember, the velocity of a wave equals the frequency times the wavelength, right? V equals F lambda. Well, the speed of light c, he could calculate it to come out with this, where mu naught, remember the value of magnetic permittivity, and then epsilon naught, right, is the permittivity of free space, right? The magnetic permeability, mu naught, permeability, and then the electric constant, permittivity. So much amazing stuff, but this is like a conceptual thing, right? You don't see a lot of math here on this particular page. And part of it is because the math is best done using vector calculus, which is not in the scope of this course. So in the part, you don't really want to memorize all this stuff anyway. So the point is, you want to know how this works. Light is the electromagnetic wave that has such wavelengths that can be detected by eyes, right? Wow. Let's pause and think about this again conceptually. This is really important. Anytime you have changing electric fields, like from an AC circuit or something like that, every time you have changing electric field, you also have changing magnetic fields. And this alternation of changing electric and changing magnetic fields, right? When you have a strong electric field, you have a weak magnetic field. You have a weak magnetic field, a weak electric field, you have a strong magnetic field. And you have this kind of continuous alternation, right? And the waves are perpendicular to one another. This is what happens when you do the vector calculus thing with the right-hand rule and all that, right? What happens is you have this continuous back, forth, and you're basically creating waves, just as if you were like thumping a pond, or you're playing a whole bunch of different musical instruments, right? You're changing the density of the air every time you play your instrument, and the change causes this variation, and therefore these waves go out. Electromagnetic waves happen too. And the thing is, electromagnetic waves, usually, the vast majority of electromagnetic waves, you can't see, okay? But there are some electromagnetic waves that you can see. Your eyes actually see them. when I'm looking at this light bulb over here, or looking near the light bulb, because I don't want to look at the light bulb and hurt my eye. And looking near the light bulb, what's really happening is you see the waves of electromagnetic stuff happening inside that circuit. That hot thing there is actually sending stuff out into space. And it happens to hit my eye. It hits my hand. My hand can't detect it, right? I mean, I can't, if I'm not looking at it, I can't tell that a light is shining on my hand. But I can tell that it's shining if I'm looking at it in that area with my eye. What I'm seeing with my eye and my hand is that that thing bounces off my hand and into my eyes, right? So electromagnetic waves, much like sound waves, bounce around. They also superimpose upon one another, and they carry energy. They carry a little tiny bit of energy, but they carry energy nonetheless. Those of you who have taken already a Physics 1, such as a Physics 116, for example, here you will, or you may remember that the amount of power, the amount of energy that's hitting our ears from sound is very, very small. Maybe a billionth of a watt per second, maybe a trillionth of a watt per second. Very, very quiet. It's not a lot of power. But that little tiny bit is enough to vibrate my eardrums, to send electrical signals through my nervous system, and thus create, one of those action potentials. They're all action potentials, everybody. Every nerve basically depends on action potentials. So you know. So all this electromagnetism you're learning, yeah, totally nervous system stuff. Anyway, all of that stuff comes when you little tiny bit of power, very, very small, right? Remember that if I have my water bottle, right? Oh, this is mostly full today, so I'm gonna drink a little bit. When this water bottle, right, is only 1/5 full, or in this case, it's about 4/5 full. So if I'm going to take this water bottle, just 4/5 full, therefore is a mass of about 400 grams, and I lift it 25 centimeters, a quarter of a meter, okay, and I let it drop in my hand, right? That's 1 joule of kinetic energy that this bottle of water had as it hit my hand, roughly, right? So if I did that once per second, boom, ba da, boom, da da, boom, ba da da, boom, ba da. That's 1 joule per second of mechanical energy, of kinetic energy, or 1 watt, right? 1 joule per second, 1 watt of kinetic energy. We were talking about watts of electrical energy. Remember, when you have a joule per second, that's because you've got electrons flowing, right? And they're being forced through with like an electromotive force or with an electric potential, right? Causing the charged particles to move as a result. And so each charge is carrying with it a certain amount of energy, right? And that's voltage, joules per coulomb. And then if you have a number of coulombs per second, you multiply those together, right? The intensity or the current times the electromotive force or the electric potential, otherwise known as voltage, right? And then you have VI equals P, the power. But these electromagnetic waves, right? And the acoustic waves, remember, we're not talking about a joule per second. We're not even talking about a hundredth of a joule per second, like that kind of. We're talking about billionths of joules per second, maybe trillions, little tiny bits. So the waves come in this way. I mean, I don't feel them in my hand, like thum, 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 thum. They're not actually hurting me or anything. These waves are running into me, but I'm not really experiencing that much, but they're there. And we can take advantage of them because, for example, our eyes can see that sort of stuff, right? And similarly, in the same way that, why do I get electric shock every time I touch my cell phone, even though my cell phone is an electrical device and it's using electron fields and magnetic fields all the time, right? I was just saying earlier in this lecture, right? It's because that stuff is very, very low in power and energy. But that low power energy does not mean that it's not useful. It is extremely useful and extremely powerful. And that's what we're going next. Does that make sense? That's what you want to understand. And so these waves really exist and continue. All right, I'm just going to finish up this lecture here about these conceptual ideas. There'll be a little bit of calculation on your study guides. I hope you're filling out your study guides, right? But really the key for this lecture is to understand how these circuits work. Look at what Heinrich Hertz did. Remember I mentioned this to you earlier? Heinrich Hertz took Maxwell's equations and kind of worked them further and did it better. Well, I don't want to say better, but it did it in such a way that that's what we're doing today. Remember that James Clerk Maxwell died at age 48, unfortunately, right, in 1879. This guy, Heinrich Hertz, man, He died even younger. He was only 37 years old when he died. And so that was kind of a bummer. But nevertheless, in his youth, he was still performing experiments, and then he took the mathematical aspect of stuff. So he took that RLC circuit that we were just talking about in the previous lecture, right? He put it at a certain frequency, got its resonance frequency going, and then connected it to this loop of wire. What happened was then he sent high voltage, sparks across here, okay? And what happened? When he produced the sparks, they were visible evidence that this had current in the circuit, and it generated electromagnetic waves. Then you can actually get another thing, right? Another kind of circuit that has just the right RLC circuit, which means it has the same resonant frequency, which means if you're sending electromagnetic waves this way, then it will receive an electromagnetic wave this way and actually be able to say, oh yeah, that's the same resonance that allows us to sort of see each other's signals. In other words, that resonance is almost like saying, well, that light shining at my eye, I have an eye, I can detect that particular wavelength of light coming this way, okay? And there you go. And that's basically, everybody, the radio. How do radio receivers work? It's because of that kind of thing. The resonances, the waves, right? The resonance frequencies, the oscillations of something going to another direction. And you can find out, wow, these are electromagnetic waves. But his electromagnetic waves were not waves you could see with our eyes, not waves you could feel with our hands. They were radio waves, right? And that's how we have radio communications today. And then later on, you probably heard of a guy named Guillermo Marconi, right? Marconi invented the actual radio that we use today. Heinrich Hertz was a guy who established and did the experimental aspect work on how all that works. It's great. And then today, everything. We have all kinds of stuff that we do all the time. Nuclear magnetism, MRI, right? NMR, all these kinds of things. Electromagnetic stuff. So important, everything. But we still have so much physics to go to talk about these wonderful, wonderful, wonderful electromagnetic waves that we call light, right? And remember that there's visible light and there's invisible light. We're going to get all into that in the next lecture and then get into it and talk about the energy in these waves. It's amazing. It's super, super cool. All right, we'll talk about it. I gotta wrap this up. Everybody, go to your study guides. I hope you've been filling them out. And again, if you want to review, go back and review some of those things that I mentioned before. Okay, some of the YouTube resources and so forth about oscillations, about simple harmonic motion, about waves, that kind of thing. Make sure to get those things in there. Okay, because we're going to launch in the next lecture about waves. We're going to do waves. Do the wave. Woo, waving, yeah. All right, electromagnetic waves, to be precise. Thank you so much. If any questions, ask me, ask your recitation instructor, ask your lab instructor. We'll see you in the next lecture. Bye. Thanks.